Good morning, this is Deep Generative Model. In previous weeks, we have introduced models like auto-regressive models and a simpler one like autoencoders. We are going to keep to introduce more different kind of models. In this week, we're going to introduce 3 different kind of models, specifically Variational Autoencoder, VQVAE, and Generative Flow. Each of these models has their own interesting part. For the Variational Autoencoder, as the way we introduce it, we'll start from a mathematical formula that has nothing to do with the autoencoders. But after we do some derivations, you'll find the structure of autoencoders came out. And the VQVAE is a way to represent the things, the objects, into a spatial latent space, which is the discrete latent space. And it can be considered as a method that can solve some common issues that appears very often frequently when we wish to design a network architecture of the autoencoders. And the VQ alone is a very interesting and useful part of designing neural networks. The generative flow is an interesting idea and a beautiful formula, can be beautifully formulated in mathematical. But the most interesting part of the generative flow is that it could be the next big things, just like diffusion models or GAN or large language models. In 3 or 4 or even I think it's 4 years ago, we have already introduced the diffusion models along with generative flows and other models. But one of the important models we introduced 4 years ago in this course is the diffusion models, and we have already said that it is a promising method for doing the generative models. Even though back then, generative adversarial networks is the single most successful image and popular generative models for generating images and maybe videos or musics. But back then, we can already see some works that showing the potentials of the diffusion models. And just like diffusion models, generative flow models has a huge potential, and we're not saying we are expecting to see it going to be successful, but there are some chance that it is going to be very useful, at least very useful in certain fields. Okay, so although these 3 models are not as trending or super popular like the diffusion models or large language models or like the generative adversarial models before, but they, just like we said, they have their own interesting aspect, and by familiar with more different kind of different ways for generating contents or to design the generative models. Later on, we are going to, when we introduce those models like diffusion models, you have a reference to compare with, so that you can see the interesting part or the advantage of each of these different models. Okay, so we're going to start with the variational autoencoders. And this is the first one we are going to introduce. It is going to have a lot of some of the mathematical calculations and formulas. So that's why we are working with a tablet and the lecture note itself, because we can show more of the mathematical formulas. So the major reference of this work is this one. So this one is a very good introductory paper, article to review the history or the motivations of variational autoencoder. We're going to follow this one, and if you click this link, you can just simply get to these articles. This one has been updated at least until the 2021, and the other one is also a tutorial or a summarize of the works of autoencoders, because I mean for the variational autoencoders, because there has been a very long history of variational autoencoder. So it has some good works to summarize the history, motivations, and all the intuitions behind this algorithm. So you don't have to go back to the original papers. These two articles are very useful, and if you are trying to, or you wish to get more familiar with variational autoencoders. Okay, so we start from the setting. It's like what we have introduced before, that what a generative model is. So we are start from the X is what we are trying to generate. So for example, if we are trying to generate images, this is a space that contains many different kind of images. So if we are generating MNIST like images, MNIST is handwritten digits dataset. So it will be a space that looks like R28 times 28, a vector space, because the size of MNIST image is 28 by 28. So it can be considered as a vector space. So this is our X. So we're having a procedure which is called F. It contains some parameters which we denote it by theta. In the field of neural networks or machine learnings, we may call it weight. So it is parameter, or you can call it weight. And Z is a random variable that gives us some randomness. So in general, it is often considered Z. One of the particular interesting example of Z is the normal distribution. Usually we consider the normal distribution in a higher dimensional space. So the bell curve is the one-dimensional normal distribution, but usually we consider the multivariate normal distribution that appears in a higher dimensional space. In a two-dimensional space, we usually visualize the normal distribution as a circle. It actually looks, if you look at it three-dimensionally, it still looks like a bell curve or a bell-shaped things, like this one. But if we consider the density of it, so it is like a circle. The center of the circle is the mean of this normal distribution, and it's going to be very dense around the center. But while the radius increasing, it becomes sparse and sparse. Okay, so the idea is we are trying to, from some distribution that we already know, for example, like just I said, the the normal distribution. I'm putting it in a one-dimensional way, but usually we are considering at least two-dimensional. But I'm using this to denote the normal distribution. So by taking z from here, then we are putting this z as an input of a function f. This function has some parameter theta that we wish to decide by using some machine learning procedure to find the best theta. But assume we have already one theta, then we are trying to fit this z as an input of this f theta, and we're getting the result in the space of X, which might be an image. Okay, that's the basic idea. So how do we measure, or how do we training to find out the optimal theta? We have some loss function in order to, so in a concept we are trying to select the best theta out of all possible thetas. But the meaning, we have to decide what is the meaning of the best one. So usually we have a loss function, and this loss function or some kind of score. So either we have the theta to have a higher score, or to have the highest score, or we have to minimize the loss. So usually score or loss are pretty much indicate the similar things. The only difference is usually the score is higher the better, and the loss is lower the better. So one way to find out the good to measure how good our result is the likelihood. Is using the likelihood. So maximum likelihood is one way to do so. So likelihood is a way to, we have already mentioned before probably. So likelihood is a way to measure how likely our sample can be seen in our model. So the idea is that we already have a model f theta, and it can generate something. We have collected some like x1, x2 image, x1, x2 or x3 already. We have already seen it. So for each theta, by fixing theta, we can compute so suppose we can compute the probability or more formally the likelihood of how possible this f can generate this guy or this image, this sample, because suppose we only have three samples, three different images, so we can estimate or compute in this model with this theta how likely this is going to be generated by this f, and how likely the second image is going to be generated by this model, and the third, how likely the third one is. We are trying to find the best theta so that the likelihood of generally the sample that we observe is as high as possible. So we usually given examples in a discrete setting, that is like throwing a coin. So we can build models like we can see the first one is head, then the second one is tail, then the third one is head and the tail, and our model is usually by considering what is the probability of the head, if it is a theta, and the probability of getting tail is 1 minus theta, and we can compute the probability this one is theta, 1 minus theta, and theta, and 1 minus theta. Then we multiply them together and to find the likelihood. However, right now we are going to deal with a continuous space. So the probability is a little bit difficult to actually compute. So the idea is we run through our latent space. Let me just call it the latent space. The Z is called the latent space, which is we start from a random distribution. Usually, like we said, it usually is a normal distribution. So the procedure kind of like we are trying to use a machine to generate something, like generate an image. But by doing so, you have to provide some random input. So maybe you are throwing a coin or throwing a dice, rolling a dice. And this Z is the dice or coin that you are throwing. So we already know the probability space of the dice, assuming we have already know what the probability of getting a head or tail or getting each dot or each side of a dice. So we're starting from some random space that we already know, and we're trying to see what is the resulting space, the probability of this resulting space. So to do so, we'll consider this Z, especially when we consider this Z to be in as a normal distribution. So it is a normal variable. So it is the range of this Z is in a continuous space. So we have to do the integration over this Z, and to find out, we have already fixed the theta, and we have to find out what Pxz is. By given any Z, what is the probability of getting sum of X? So this formula, especially this one, is actually hinted that our algorithm of from Z to get X is some kind of stochastic way to get that, not a deterministic one like what we are doing for neural networks. So I'm giving you one example, or actually two examples for what the Pxz might be. So one way to do that is we use a neural network f z theta to get the mean, and we fix a non already prefixed standard deviation. This one is actually variation, and we are giving this one to as a parameter of this normal distribution. So in this way, we have a neural network that can generate fixed thing, deterministic thing for given input, but we can still generate some stochastic or randomness output, because we are getting what we are getting is distribution. So after we get this one distribution for this Z, of course we have already fixed this theta, and given some Z, we will get this distribution. Then we sample our X from this distribution. So let me put it more in a more concrete, specific way of saying what this formula is. This formula, in practice, it is pretty much just saying, so suppose we are generating an image, so we are giving a Z, and it is actually generating some image like this one. But we are not simply output this image. We are outputting something that has a we are outputting some normal distribution that has a mean as this image. So what does this distribution looks like? It actually is as simple as this image plus some noise. This noise, because of this covariate structure, because it is a diagonal. Or this one is actually is a matrix that looks like square. This one a zero. The zero means each one of them are independent. Each of the elements are independent, and this one means they are all have, for each one of them, they have all the same variation, and of course the standard deviation as well. So we are simply adding some noise to the image that, which is fz theta. We are simply adding some independent noise that are also normal and have the variation as this one. So that's it. That's the what it actually do. So in practice, we probably do not wish to actually add this noise to the actual generated images. However, this randomized setting may help us to do some calculations. Okay, and another way to do that is consider the output is a Bernoulli distribution, which is simply as like the throwing coin distribution, flipping coin distribution. So the theta is like P1 is maybe theta, and the P0 is 1 minus theta. So you can use this one as well. If the generated image is binarized, you only have 0 or 1 value, you have only white or black points. If that is the case, you can use this output as well. So your theta might be this theta is not this theta, is your let me put it into another variable name. So maybe P 1 is equal to f the theta, and P for each of pixel we have a P0 is equal to f the theta 1 minus 8. Okay, so there are many ways that we can generate some distribution and sample it from it. So okay, let me put this one, I mean not this one, this one more specifically. So the thing is that you generate an image, but our target image is often or most likely is just for each pixel it is either black or either white. So we're mostly dealing with a binarized image. However, what is our output? Our output is something that is not exactly black and white. It has a probability like this one. So maybe some of them have more gray part like this one. But still, each of the pixels are independent. So the intensity or the lightness, I cannot put something that is not either full blue or white, but you may imagine that they have some different grayscale in this one. So the output is something like a grayscale image, and if the white, if it is total white, it means the 100% this pixel is going to be a white. So if it is half white and half black, then it probably means that the half of probability it is going to be 1, and the other case, the other half of probability is going to be 0. So that is how the whole thing is going to be. Okay, so there are two issues. How do we choose Z? Although we are giving an example that and also hinted that most of the time we're just choosing a standard normal distribution, but the question is, does standard distribution, I mean standard normal distribution, good enough? And the second one is, okay, suppose we are using the standard normal distribution, how to actually calculate the probability. So the first question, the answer is usually yes, it is enough. To illustrate this might not be an issue for you, but for someone that is kind of familiar with mathematics, it might think it is very difficult to use a standard normal distribution to mimic all kind of distribution, because we usually, like I say, we usually imagine the standard the normal distribution as especially the standard one as a disk, and consider if we wish to transform this disk into this ring, is it possible? This one is impossible if we are considering a topological transformation. The one thing is this one, they are not topological equivalent because this one has a hole inside it and this one does not. When we say topological, the intuition is that we can actually kind of squeal and make it flexible of it. In the more formal way saying it is we have a continuous transformation from here, this guy, from left to right, and also the inverse is also continuous. That is a formal definition, and we know that if we consider this kind of continuous and the transformation which also has a continuous inverse, then we cannot transform a disk into a ring. It is impossible. They have some fundamental differences between them. So this one is because usually we are kind of acknowledge that normal distribution into a disk, although it's not, but if you have a threshold or binarize it, it will sort of become a disk. And this one is actually a ring. So is it possible to transform the left one into a right one by f? It is even possible. The thing is, it is possible. This one is a formula. We can simply normalize each of vector and put on keep some of the randomness, so we can easily have this one. The catch is when z is 0, this one does not work. However, if the probability is our concern, we don't need to worry too much about it because the chance that z is going to be exactly 0 is very small. It actually is 0 because it is just 1 point. So we don't need to worry too much about this special case. Not unlike the case that we have to transform a disk into a ring by the continuous mapping forth and back. This one is impossible. We have to consider the center one. So if we can ignore the center pixel, the single point, then it can become this one. But that was not the question. However, in the setting of the probability distribution, that is not a thing that we need to worry about it. So we can freely generate from this one to this one. And in fact, we can imagine and I actually find a lot of different. If we are creative enough and knowing enough mathematics, you can actually transform this guy into a lot of very different shapes. So in general, we are not worried about this. So z can be simply we can just choose z can simply to be the normal distribution. So at least this one is at least not an immediate difficulty to us. So we can at least we can start from a normal distribution. That is okay. I can imagine that in certain applications, you can choose a better distribution than the standard normal distribution. But in general case, it is not a bad choice, and it is as good as other choice. And plus, we have already mathematicians, statisticians, and physicists has already dealing with the normal distribution a lot. So we know a lot of probabilities of this distribution. So happy to work with normal distributions. So why not? So we are using. So the answer is how to choose Z, which simply choose normal distribution. It doesn't matter that much. So we choose the standard normal distribution. Of course, this is a multivariate one, so it is lives in a higher dimension. So the second issue is how do we actually calculate the likelihood. The naive way to do that is maybe we can just simply sample a lot of different Z and to get so because we can actually generate infinitely many Z, and we try to feed this Z into the neural network or the model you have already get so far, and we can like 1,000, 10,000 Z, and we can actually estimate the probability of this guy. But this one is very, very difficult and actually invisible. The thing is, this one is basically discretized of integration. So when we think about the numerical integration, it's something like this one. And we put it into several different part. So the simplest way is simply to choose any one of them, to sample any point in every segment, and we calculate this approximation. If we split this partition to be fine enough, so each one is small enough, then we can have an arbitrary accurate approximation of this integration. This works actually just fine for one-dimensional integration. However, because of the curse of dimensionalities, if you are trying to work with a higher dimension, so say a three-dimensional world, if you wish to do the same partition, like if you wish to do the 10 or maybe 100 splits in each dimension, you actually need to do is 100 times 100 times 100, which is like 100 actually 1 million samples. You require to do the 1 million sample if you are trying to do it things in three-dimensional. And in fact, if we wish to generate a image or even higher dimension things, this is going to be very, very inefficient to do so. And in practice, how do you actually compute this guy? The X is so suppose we are generating some images, just say for example, to generate the handwritten digits like MNIST. The actual way to do this guy is we actually find all these different kind of x1, x2. Basically, these guys are like 1, 0, 7, 6, 5, all this kind of image, and we randomly this is the like we say as a latent. Maybe we choose like 1 million these latents, and we compute how likely because we already have just like we said, given this fz, we are generating some images. We can actually compute because we already got a distribution like this one, fz square times this one is constant. So we can actually compute pxz by fixing any z. We can actually do that, but most of the time it is going to be very small because the probability of, suppose this one looks like this one or something like this one. The probability of this one is because remember that this model we actually says that in practice it is just this guy plus some noise. So the probability of this one px and given this z is the probability that we add some random noise and to make this image become this one. So most of the time it is going to be almost zero, because it's very unlikely to actually to add some noise and make this noise to be exactly like this guy. So most of the time, this one is 0, this one is 0, this one is 0. It is very, very difficult to hit the actually something that is non-zero. So you will need a lot of really, really large different z to make actually to make this computation accurate enough. So you may ask, okay, do I actually even need this accurate precision to calculate this probability? Maybe we can just calculate something roughly, not that accurate, but have certain accuracy that might be just enough. The thing is, it is not enough. This is because usually we are going to use mean square error, and we'll find out that we're going to actually use mean square error if we are assuming that the output is in normal distribution, like what we just did. It actually estimate, it's actually just some kind of turn out to be some kind of mean square error. So if we are using mean square error for this example, suppose A is our target, is a ground truth is a target, and B is something, and B and C are something that the model generated. You can actually find that, I mean, of course we think C is a better match for A, but pixel-wise, B is a lot of similar to A than C, because C has position differences, and although they look similar, their mean square error is a lot bigger than the mean square error of B and A. So and the differences between B and A are actually quite small, although they are not something we actually want. So we have to have a very accurate estimation in order to make all these things work. And even though if you can, I mean, it is certainly possible if you use two-dimensional latent space, which we will see later. We can actually use two-dimensional vector space, latent space actually, latent space. However, okay, so suppose 1 million sample has some can have some decent accuracy for this estimation. This one requires is required for each mini batch. So you are going to need a lot of I mean, if you think 1 million, suppose 1 million sample is enough. This 1 million will only give you one loss function, and this loss function is just can be contributed to at most one step of the optimizer for the gradient descent. So if you have to train it for like 1 million steps, you will need literally millions of million samples. That is very, very inefficient at least, and most likely it is invisible. So we are going to need a more efficient way to actually to do the estimation. Okay, so one way to do that is to do a more efficient sampling, or to do a more efficient sampling. So suppose I'm going to give you a more real life like example. So suppose we are trying to find out what is the percentage of people that can jump and reach his hand can reach, he can jump and reach like say, I don't know, 2 meter, and I don't say. I'm not sure it is, how difficult it is. Suppose it is difficult. Suppose this one is difficult. If you can, let me make it more difficult. Like 2 meter and a half, 2 meter and 250 centimeter. Okay. So the question is, how many people are going to reach this height if when he jump, and his hand can reach this height? So we want to know how possible. Suppose this is very, very difficult. So like no more than 1% person in Taiwan can do that. So if we are doing this sample and sampling like 1,000 people in Taiwan, so Taiwan has like 20 million, almost more than 20 million people. So if we simply sample like 1,000 people, then the sampling, the result might not be very accurate, because there are only just one, say, one person in 1,000 that can reach this kind of height when they jump. Then if we simply sample 1,000 people, chances are there are just one or maybe zero people, a lot, like 30% of time, they are like nobody is going to reach this height. So we are going to sample more people in order to get a more accurate estimate. So we will have a more efficient. We should have a more efficient way to do the sampling, to do the pooling. So how about this one? Let me go back to it here. So how about if we do the sampling like this one? So suppose we divide people into several groups by height. So like 150 cm, 160 cm, and below. This one is one. First group, second group, and third group, 170, 180, 190, 200. 1, 2, 3, 4, 5, 6, 7, 8. So I probably should put it into like 10 groups. Okay, so it might be easier to do so. So suppose I'm doing the sampling like this one. I'm sampling the guys with 210 total than 210 centimeter, and we put in 100 people out of all the people that in Taiwan, that is the height of them is between 200 and 210, and also select like 100 people between 190 and 200, and so on. We are going to sampling like 800 people. So chances are there are many people in this sampling. They are going to, I also suspect that more than one people that can reach the height of like 250 cm. It is because we are sampling more people that has that is, we are sampling more tall people than short people, because we are hypothesize that we are assuming that more people, tall people are easier. Taller, if people is taller, then they have a better chance to actually jump higher and reach higher object. So maybe when we do this kind of sampling, 100, 100, and 100, each group we put 100 people. Although we didn't even pick 1,000 people, this sampling might be more efficient. Of course, we can not just simply say, okay, suppose we only got like there are like 300 people out of these 800 people to be can reach the target. Maybe some shorter people that can jump really high, and can actually the target. But just say that there are 300 people that can actually, out of these 800 people that can actually reach the 250 cm. So we cannot simply get the result that, okay, there, if you randomly pick one person in Taiwan, then there are almost 40%, over than 40% chance, no, like more than 35% of chance that they can reach the 250 cm. It's not the case, because we have to do the normalizer, because because we can have another talk that information that we already know that how many percent of people that are actually higher than 210, and we can actually know the real percentage of people that in Taiwan fall into this group, and how many of them are in this group, and how many of them are in this group. So we can calibrate and recalculate the actual result. But because we are more focusing on the people that are more likely to have a positive result, and we are pretty much assuming most of them, or maybe less than 0.1 percentage of them can actually reach the target. So we give this proportion of sampling for this group of shorter people. So we can have a more efficient estimation, or we can have a more accurate estimation, because we can have a more efficient sampling. So the idea of variational autoencoder is pretty much the same. Because most of the PXZ is just very, very near to 0, we are trying to find a more efficient sampling. So we call it, this sampling is Q. So this sampling depends on the target of image. So given an image, we are trying to find a Z that is more likely than a random pick of Z, that PXZ is greater. So we are trying to find a QZ that is a more efficient sampling, just like the sort of near real life example we gave before. If we wish to sampling how many people can reach the high 250 cm by jumping, we are trying to sample more taller people, because we assume they are more likely to achieve the goal, and there are not many people can achieve the goal. So by this kind of sampling, we have a more efficiently sample people that are more relevant. So of course we need to calibrate the result, instead of using the original raw result, like the 300 over 800. So we have to calibrate the result. So we have to do some calculation. So the following are some calculations. So basically we wish this one to be as close as possible, because by assuming that our sampling is perfect, so that is going to be very, very efficient. We only pick people that is going to can actually generate something near to X. Okay, so by doing the calculation, so first of all, let us to recall the definition of Kerr divergence. So not exactly the recall, but this one is a definition of Kerr divergence. We are going to go to more details about Kerr divergence when we talk about the generative adversarial networks. But to put it simply, Kerr divergence is a way to measure the difference between one distribution to another. So because our goal is to actually trying to find a sampling that can reconstruct our true distribution as close as possible. So it makes sense to have some measurement of the differences between two distributions, or to check how similar two distribution is. So one way to do that, and one of the standard way to do that, is to using the Kerr divergence. The definition of Kerr divergence is the difference between, it is not symmetric, but so which means D, Q, P, these two guys is not the same. So, but basically, this you can see that P log P, or if we ignore this guy, this one is simply the entropy, and this guy, P log Q, this one is the cross entropy. This one is the cross entropy. So, simply put, the Kerr divergence is the difference between the entropy and the cross entropy. Because this one is, the entropy is always larger than the cross entropy. It's kind of intuitive and reasonable, because you see that px, when px is bigger, log px is getting bigger. When it is smaller, it is getting smaller. So they have the same. So when, and also px and qx are all probability distribution. So the integration of it over its domain is going to be 1. So it makes sense if we give the larger one the more portion, and the smaller px the small portion, it is going to be very big. So the same thing does not happen to the qx. So it makes sense that cross entropy is smaller than the entropy itself. So this one is always non-negative. So the best thing you can do is, when qx is equal to px, it's going to be 0. Okay, so we are actually consider to compare q z x to q z p z x, this guy and this guy. But to make the, for the sake of simplicity, because we have to write this x a lot, so kind of omit this x in this calculation, and we'll put it back. So, but you can actually think this one is qzx, but it is just some distribution of z, and it doesn't matter whether we have this one or not. The calculation is exactly the same. Okay, so if we wish to calculate this Kerr divergence, by the definition, it is going to calculate this guy. We can actually expand this one into 3 terms because of the base rule. This is just a base formula right here. So because of the log, it becomes 3 different terms. So basically, we put this one into these 3 terms, and these terms does not have z, so we can move out it from the expansion formula, and because it is not dependent on z. Okay, and then observe that this guy and let me see, and this guy is in fact, also by definition of Kerr divergence, is the Kerr divergence of these 2 guys. Okay, so we kind of reformulate this, write this by these observations. So we have log px minus this guy. So we move this back to here and put a minus sign here. So we got this one. And on the right hand side, these 2 guys become these guys, and these guys, we keep these guys here. So this is just a simple rewritten of the original formula, but we are doing actually putting the right hand side and the left side this formula, these terms into a right or left deliberately. It's not just a simple written formula. We are putting them left or right deliberately. So let's first put back the QZ back to a QZ right here. Okay, so let's first observe the left hand side. This one is the likelihood we wish to calculate, PS. So that's no problem. This is something we wish to calculate. This one is the differences between QZX and PZX. So our goal, because this one is likelihood, log likelihood, which one we want to be bigger as possible. This one is going to, we wish they are because we wish they to be more similar, so we should this one to be as small as possible, because we only wish to pick those relevant or important ones. We wish to pick the Z that matters, so this one we wish them to be as close as possible. So combine this one, they have the same goal to make this term to be bigger. So although our goal is to compute the likelihood, but instead, in variational autoencoder, we change our target or loss function to be this guy. Actually, this is not a loss function; it is a score, because higher is better. Higher is better. So although this one is not exactly the original target we wish to be optimized, but observe that log px, which is the likelihood we initially wish to compute, this one is actually greater than this guy. And you can see that if we make this bigger and bigger, this one is no less than this one. So although we are not optimize this guy directly, we are optimize this guy. Suppose we can do so by simplify the right hand side. Although we are not optimize this guy, we are optimize this one. We can at least make sure that suppose this one is, let's say, greater than 10. This one is equal to 10. We don't know what log px is, but we know this is at least 10. So that might be good enough, because at least it's so if we keep getting this bigger and bigger, this one at least will have a lower bound of this one. Okay, so this kind of optimization actually has a name called the ELBO. ELBO. You will encounter this word later. ELBO, which is evidence lower bound optimization. So this one is called the ELBO. Or I'm not showing this. This might be a bound. I'm not sure what it stands for, but usually it's in short it's called ELBO. ELBO. Okay, so it remains to find out what the right hand side is. The strategy is, instead of directly optimize the left hand side, the right hand side should be easier to compute. So let's first observe that we actually got our autoencoder architecture right here. So Q is actually, as the architecture for autoencoder, Q is actually the let me check. Okay, Q is the encoder. So Q is something that when we put X into it, it will return some Z. get the output of Z, and P is actually the decoder. So given latent Z, it will generate the X. So this one is the decoder, and this one is the encoder. So by looking for the first term, it is actually, so you see that what does it mean by Z? Taking this notation or this formula means we are using Q to get a Z. So Q is considered as a distribution, but what exactly Q is? So you can consider this encoder. So we are given X from the training data, or getting an X from the training data, and by doing some procedure, we generate a Z here. So we're getting a little bit detail, but you can consider this is a neural network. There's neural network. We feed into an image into the neural network, and we'll get some distribution of Z. And after we get this Z, we generate this X and compute the likelihood. So the likelihood, which we'll turn out to see later, just a bit later, is simply a mean square error. So this whole thing is pretty much exactly like the autoencoder is. So this one, let me repeat it again. By given an X, we get a Z, and we get a Z and feed it into and generate an X and compute the log likelihood. So suppose the log likelihood is, the PX is, we are using a normal distribution. The log likelihood is exactly up to a scale. It's simply the mean square error. So this one is pretty easy because this one is autoencoder. There are some considerations, but this one is pretty much the same as autoencoder. So how about the other one? So about the other part, the second term. So this one is a computation of the KL divergence. This one is a computation of a KL divergence. This guy is, we have already decided it to be the standard normal distribution. Okay, so this no problem what P is, and we only need to find out what QZX is and to compute the KL divergence, because both of them, like we said, the QZX is actually is also a normal distribution, which we use a neural network to generate. We haven't mentioned before, but because normal distribution is easier to compute, so one way and the standard way to do so is we use the neural network to compute a mean and compute the variation, and use them as a parameter to construct a new normal distribution right here. Okay, so this one is also a normal distribution. So there we have, like we said before, people studied the normal distribution extensively. So there are not a lot of results about the normal distribution. So no surprise that we already know how to compute the KL divergence between two normal distributions. So the formula is in fact this guy. So suppose we already know two normal distribution. Of course, by saying we know what the normal distribution is, we mean we know the mean and the variance of these two distributions. So by using these four guys, we can actually compute the KL divergence between these two normal distributions. So in our case, this guy is 0 and this guy is I. So it makes it much easier to compute because sigma 1 is I. So this guy is simply nothing. And because mu 1 is 0, so it is just nothing. We don't have, because we have two negative becoming one positive. So this one is simply mu 0 dot mu the dot production of this, the inner production of these two guys. So it's right here, and this one is I, so determinant is just 1, so it becomes negative and nothing here. So we got this guy, and because this one is I, so we save the trouble to compute the inverse of the metric. So it's just a trace of this guy. So that's it. So after, and we can get everything from, because we already computed it, so we can get everything from the output of this neural network. So there's nothing, this is standard to compute all these so care divergence. So we have two parts of our loss, or actually our optimizing target. So one is pretty much the same as the autoencoder, we'll see a little bit later, and the other one is, we just mentioned, the care diversion part. The care diversion part is pretty straightforward to compute, and that one is the only difference between the autoencoder. Although even if we don't consider this care diversion, by doing all this computation, we have an idea of what the loss of the autoencoder is. So let's go to the autoencoder part. By assuming, because the output is something like this one, if we are using a normal distribution, the log of this guy, because the normal distribution is something like 2 pi something, I don't remember, and negative square and x minus mu, something like this one square. So by taking a log, this one becomes some constant right here. Very difficult, very complicated, a little bit too complicated. I cannot remember a constant, but this one is a constant. And by taking a log, this one is gone. So we got something like this one. And you can see that because this one is a constant, this one is also a constant, this guy is constant, this guy is also a constant. So it's pretty much just as the mean square error. Okay, so for the implementation, there's one terminology that might need to be added to your knowledge base or your dictionary. That is the reparametrization trick. This one is not difficult, but I think this terminology is very useful for communicate with other people. So the purpose of this one is kind of silly, because we usually say some simple, like when we already got the encoder and get a distribution. Actually, it's right here. I mean, in the most straightforward explanation is that we got a distribution right here, and we sample a z from this distribution. But what does it exactly mean by sampling some z from this distribution? And how do we even do the gradient descent over this kind of thing? So that seems to be almost either impossible or make no sense at all. So the standard implementation is like this one. Instead of doing sampling, we consider epsilon as an input, a new random variable epsilon, which comes from a standard normal distribution. And after we compute mu and the sigma, we simply make the z to become sigma x times epsilon plus the mu. So although sigma itself, I mean z itself is not a independent or totally fresh newly constructed random variable. It is a random variable depends on epsilon, which, however, the distribution of z is exactly the distribution that we wish to have. So that's it. I think even if you never heard of the term parameterization trick, if I ask you to implement the variational autoencoder by the knowledge of the above introduction, you might come up with the same solution, because I don't even imagine another way to implement it. It might be just even if I can imagine some other way to implement it, this one might be the most standard, obvious, straightforward way to do so. So I have a trouble to understand why this has to have a name, but the fact, there's no other way to go. But it is still nice if you understand or knowledge that this terminology, parameterization trick. When people say about this trick, you don't need to afraid. There's nothing to need to worry about. It just simply says, okay, I have an implementation, and instead of using the sampling itself, I'm using a way that to separate the sampling it into as an input, and there's no need to worry about the gradient descent or back propagations at all. Okay, so of course you can also act some conditional into the variational encoder. I'm not going to go into detail because we have a lot of stuff to cover, but there are some, and maybe I think you can come up with how to incorporate with condition into this network. There are some straightforward or obvious way to do so, but anyway, if you really wish to read, there you can see the link article in the above of this note. But I think the more important thing to do is, although I'm not putting it as a homework because I have a controlling of the total number of homeworks in this semester. However, I encourage you to try this example. There's another one example for the generative flow, which was also homework, but not in this semester. So anyway, there are some implementation right here, and you can try to generate the variational autoencoder for to train a variational autoencoder for generating digits in MNIST, and try to do so with the latent dimension, especially for dimension 2. When I say 2, I mean the encoder you generate one mu1, the mu2, and the sigma 1 and the sigma 2. Actually, sigma 1 and the sigma 2. Maybe you need a little bit correlations. I kind of forget. Okay. In general, we just generate the diagonal, or we generate a diagonal. Okay, so you generate this mu1, mu2, and the sigma, the two-dimensional sigma. However, just ignore this by ignoring sigma. So our dimension is latent space is just has two-dimensional. So it is very interesting. You can actually plot all the generated image on this latent, and to see how this image affected by the latent. So you can see that it transforms smoothly, and how this two-dimensional affect the actually generated images. That is very interesting to see this grid. This can be only done if you are trying to use a latent space of two-dimensional latent space. This is kind of difficult to do so if you are using a vanilla or just using a standard autoencoder, because it's kind of difficult to squeeze the latent dimension into two. It's very difficult to actually train it, but I think that the variational autoencoder has some advantage. So it's not too difficult. It's kind of standard to actually you can reduce the latent dimension into two, and you can have this nice image and visualization of what actually happened between latent and the generated image. Another thing that you can see is because also you have a two-dimensional latent. Although our training does not use any information of labeling, still we can plot the latent space and coloring the samples by their labels. So you can see that although we didn't feed the latent information, label information, the label is also usually the digit represented by these images. It can still have some essential meanings about these digits, because I think the digits are one of the important aspects of this or property of these images. So it actually can, although we didn't ask it to do the classification, it can still, each of these class can still have its cluster of each class. So it allows us to use this variational autoencoder as a pre-training method, and maybe later we can have various ways to use this pre-train method. Maybe use for the future learning. So since the same digits are usually have in the same group, so if we have like 10 samples in each digit, maybe we can simply just find out what the areas or regions that should be for each digit. So that will be a very interesting experience if you have tried these examples and these past homeworks. So that's about the part of variational autoencoder. So we'll do later. So next we are going to talk about the VQVAE, the vector quantized variational autoencoder. Okay, so next we are going to talk about the VQVAE. So let me go back to the lecture note and see what it is. Okay. So VQVAE itself is very recent results, unlike the variational autoencoder. So the recommended reading is the original paper. So there are two major papers about the VQVAE. First one is this one, the neural discrete representation learning, and the second one is the VQVAE2. Actually, VQVAE2. So what is vector quantization? So one way to think about it is the color quantization, because we know colors can be considered as a vector of length 3. So, but it is more easier to visualize it. So back in 1990s or early 1990s and the late 1980s, it is quite common to use color quantization, because you know that early PC or game console, it usually have a difficult time to doesn't have the ability to display all the color at once. So it usually has a palette of a limited color, like 16 color or 156 colors. It can only show a finite limited number at the screen at once. So in the realm of PC or personal computers, it is very often setting for the EGA card that you can sorry, you can use a palette of 16 colors at once. The good news is you can choose what the palette is. In some consoles like Nintendo's machines, like the older one, the Famicom or Nintendo, that is the first generation, the 8-bit machine. There are only fixed number of palette, but at least for PC, this palette you can choose any 16 number out of all the possible numbers. All the possible colors, to choose 16 of them. However, you are only limited to have 16 colors for this palette. So, for example, for these images, for this part, it has four 24-bit RGB colors. So that which means each of the channel, like red, green, blue, has 25 and 6 levels of intensity. So 8 times 3, so we got 24 bits. So however, if we are limited by using 16 colors, we have to choose the best palette for this image. So we have to choose 16 colors. So for each, after we have already choose these 16 colors, for each pixel, we choose one color out of these 16 colors to be as close as the original color as possible, so that we can reconstruct this image to be similar to the original one, but you can still see the differences. But it makes sense to think about one of the palette, consider the optimal 16 colors specifically for this image. Also, that's the idea of color quantizations. For the vector quantizations, it is pretty similar. Just that our vector is not limited to the dimension of 3 vectors. It can be a very long or arbitrary long vector. And it has been used in many different fields already before this work. This is not a new term. Okay, I lost my. I accidentally closed the tab. Okay, it's quite difficult to enter. So let me go back to the lecture note again. Okay, so let's go back to the VQ part, the vector quantization part. So it has been already used. It is not new terminology that invented by this paper. It is a very common technique that have been used in many different fields, including the signal processing part. So you can imagine one of the common technique to do so is, so if we have already got image and the colors, maybe we can simply using a k-mean algorithm to clustering these colors, and the plate of this 16 colors is the center of these k-mean clusters. So that might be the easy and straightforward way to do, or obvious way to do so. And this is in fact a good way to do maybe not the best way, depends on the situation. So it all depends on the laws, but it does make sense. It does make a lot of sense. Okay, so why do we actually need the VQVAE? The thing is, it is, as we mentioned before, one of the design principle of autoencoder is, okay, we need to have a bottleneck at the latent space. So if this one is an encoder and this one is decoder, this dimension you need to have a small dimension than this the input. So your x, your z, the dimension of z must be significantly smaller than significantly smaller than the dimension of the original images like x or the thing that you wish to generate. So for the case of image, not only you need to be smaller, you need to be a lot smaller. So for example, if you have an image of like 1024 and 1024, suppose your z is something like 256 and 256. Because image has some continuities, so the real dimension of this image may not be a dimension of R 1024 times 1024. So we know that if we kind of shrink this, resize it into 522, just in half size, in width and the height, we can have a very confidence to reconstruct the image back from this resized image, because it contains most of the important image informations of this original image. Of course, it is going to be get a little blur because you know that information has actually lost. But by using some algorithm, super resolution algorithm, it's sort of robust to reconstruct the original image in some sense, at least. And we don't limit it to use the resize to reduce the information. So for example, by using compressions like JPEG or other method, we are expecting an image to be compressed into a small size. So although the image may have a higher resolution like 1024 and 1024, the real true dimension is not as huge as this one. So at least we know that if your bottleneck is like this guy, this one times this one, the half size, this is pretty safe to say that this bottleneck is not small enough. And we know that the general construction of a convolution neural network is like we reduce, for each layer, we reduce the size, the width and height to be half, but increase the channel to be twice. This is a very common and standard way to design the architecture of a convolution network. But the thing is, if we wish it to be used on an autoencoder, something like this will happen. So start from like say 128 and 128. So say this one is a black-white, a grayscale image, so it has only one channel. And as we reduce the width and height into this guy, we need to increase the channel, and not only by twice, we have to increase the channel to some reasonable number of channels, say like 32. And when we go a bit next layer, it may be some dimensions like this one, and we have to double the channel, and so on. So we go to here, and it has this guy. So you can see this guy is like 214, and this guy is 24 and 27. It is in fact larger than the original X, because for each each layer we actually only half the bandwidth of the next layer, so it go down slowly, but we have to go up rapidly at the first layer, because the image itself doesn't have enough channel. So the design is quite difficult, because if we have to have a reasonable bottleneck, which is the latent space, we wish the latent space to be a reasonable bottleneck. It kind of limited our way to design the networks. So sometimes we wish to have more capacity to this network. It might give us some issues because we have some limitation, restriction for designing a convolution encoder and a decoder. The VQVAE can solve this problem by saying that you can use your encoder freely in any kind of architecture. You don't even need to shrink your spatial size, like width and height, into very small one, like 4x4 or 2x2. Because in experience, if you are designing an autoencoder and you are trying to make the spatial size too small, because you want to make the bottleneck to be small enough, to be reasonable small, you have to have a lot of different layers to reduce the spatial size. So if very often you are going to get like a 2x2 or 4x2 layer. But if your layer is too small, the dimension, the width and the height are too small, the quality of a generated image is going to be pretty bad. Right? However, in VQVAE, it doesn't have this kind of limitation. You can freely, you can just have any dimension of latent space. Maybe it like 16x16, 62x62, or even if you are reducing from an image like this one to something like this one, it is fine. Like typically you have a higher dimension, higher resolution image like this one, and say 128. Maybe the channel is like 500. This is totally fine. Although you may think this one is not even a bottleneck, but by using a discrete latent variable, it would be fine. So let's see how it does. The basic idea is, even though this one is like say what the example we just used, like 120, this is a dimension of the image. Also, we have an image like this one, and the dimension of each factor is 512. This one is like this D. D is equal to this one. Although this one does not seem to be a bottleneck, we can quantize it to make it practically becomes a bottleneck. The way we do it, we can simply choose like, we should simply choose 1000, K to be 1000. So we have a palette to be 1000. 1000 seems to be larger than 512, but think about it. These are just a number. So the space here is R 512. So even if we consider it has become a 8-bit space, the total configuration of this guy is about this one. And instead, here we only have 1000. This guy is far larger than this one. So this one contains much more information than this guy. We can even choose it like 10,000 or maybe 1 million. It doesn't matter. Even if we choose 1 million, 1 million is considered to be a very small in a high dimensional space. It is very sparse and contains, if you consider about the information entropy, this one is far less than this one. because if you consider the information, this one is 8 times 512. This one is how much is it? Like 4092 bits. The information contents in here is 4092 bits. If you consider like the 8-bit color in each channel, and if we choose 1000, it is just like 10 bits. Even if we choose like 1 million, 1 million is kind of like the 20 bits, much less than this guy. So we have little issues about the bottleneck things. So it will be much easier and freely for our design of architecture. You can actually freely to do it. So by controlling good enough K here, we can have no worry about the bottleneck things. Okay, so the whole architecture is like this one. First of all, we have a CNN encoder. So this is reduce it into still a two-dimensional image and some kind of a channel. The channel length is D, and you have W, H. Maybe not in this order. So in general, if you are in PyTorch, it will look like this one, batch, and D, that is the channel, and H, we start from H first, then W, it may look like this one. Okay, from this one, we are going to quantize each D by using the codebook right here. This guy is called the codebook. It's kind of like a palette or a dictionary. So for each pixel, we choose from this codebook to find the most similar one out of these K possible choices. That's it. That's it. The formula is actually in here. You can see that the reason, for each encoded pixel, we pick a cross embedding from the codebook. So that is the vector quantization process. Okay, so after you quantize it, because you still have say the batch size D, H, W kind of shape of the tensor, you can feed it into the decoder as usual. So it can work either way. If you don't have this one at all, this guy can be composed with the encoder, can be composed directly with the decoder, or you can have the quantization right here. The shape of the output is still the same, so you can. So the configuration of the tensor is exactly the same, so you can feed it into the decoder without any problem. The issue is, how do we train a model? The decoder, so we have some laws right here with because this is just simply an autoencoder, so we have some laws right here, and we can do the back propagation without any issue until we reach this code book. Because looking at the code book, the lookup table method does not have a good gradient. The gradient is actually 0. If you can define it, the gradient is mostly 0. It is actually piecewise 0, except for some boundary point. But the fact is, it does not work very well with the gradient descent. So that means you are unable to pass through the gradient to the encoder. The reason is, usually if you have something like the argmin, it does not play well with the gradient descent and back propagation. So how do we bypass this? There are many ways to do so, but one way to do that is we simply ignore this guy. to straight through, I call straight through. We have gradient right here. Instead of passing through this table lookup, we simply pass directly it to the output of here and continue to do our gradient descent, continue to do our back progression directly. Then we'll have all of our gradient needed for the optimizer. The only catch is this is not a true gradient. It is some kind of substitute, or maybe you say the estimate gradient. But it actually works, and I think it's make a lot of sense because I mean, mathematically it doesn't make much sense, but we know that it still has a property that if we wish it lost, I mean, it has still have the correct direction if we actually wish the gradient to do. So we still have this weight is higher, then we can estimate this loss to be smaller. So we can still have the correct direction most of the time. So that's why this one, I think this still works. So anyway, that's one way to do so. There are many other ways to do that, but mostly you have to estimate, because the formula doesn't work with back progression, and there's no true gradient for this kind of formula. So there's no gradient at all. If there is one, the most correct one is 0 for all this kind of thing. So that's why this one doesn't work with gradient descent. So actually, even if you doesn't consider other things, any estimation is as good as others, because there's no, in a sense, there's no true gradient values. So just give you some gradient value. And another way to think about it is, because you can actually bypass this one. This one is actually just kind of like a mask or noise added to here. So if you consider this one as an actual source of noise or mask or some kind of corruption, like what we did for the noise autoencoder, noise remove autoencoder, that is sort of like that. Okay, so we already know how to train the encoder and decoder. It remains that we don't know how to train the codebook itself. So there are many ways to do that. So for the original VQVAE, the way is pretty simple. Let me remove this one to here. I mean, scroll it to here. So this one is the actual loss for the original VQVAE or VQVAE1. So this one is a autoencoder loss. So it has the bypass, straight pass, straight through gradient, those kind of things. But we can actually do the computation, do the optimization. The thing is, what about these two guys? These one are two different errors. So SG means stop gradient, which means we only, for this formula, we only optimize this E. This E is come from the codebook. And for this formula, we only optimize the Z, the encoder itself. So the first one is a reconstruction loss, which is just the autoencoder loss. And the second one is square error to train the codebook. So it used the most obvious or straightforward way to train the codebook. We make the codebook to be as close as the encoded latent. There are two latent, it's a continuous latent and the discrete latent. So it used the naive way to simply to match the codebook to the output of the encoders as close as possible. So it will be sort of going to the center of its group, because I mean, what I mean by center is because this one is the mean square. So suppose we already know which x is going to which for which e. So suppose we fix this x1, x2, x3, and we know this one is going to be, I mean, the x1, the x2, the x3. This one is going to be converged. This e is converged to the center of this guy. So it works like the only difference. It only converge to the center. The only difference is because we are also training the encoder right here and using the reconstruction. Okay, we're using the reconstruction. And okay, we do the reconstruction. We use the reconstruction loss and use this last loss, which is called the commitment loss, actually affect the encoder. So there may be some more. So it is not as static as what I described before. So it has more dynamic into the training. But suppose every x is fixed, this is going to be the center, converge to the center of the continuous latent that is choose to be the same group as this entry of the codebook. Okay, so there are some experience setting about this one, and one thing that is interesting is why is this called the variational autoencoder? It is because we don't see any KL diversion right here, right? There's no KL diversion, which is characterize which is a major difference between a variational autoencoder and the standard autoencoder. Is the variational autoencoder has the KL diversion, but this one doesn't have. The thing is, because our latent is discrete, the KL diversion is going to be 0. So technically, it can still be considered as a variational autoencoder, but without the actually something to do with the latent space to force it into some standard distribution, like a normal distribution or something, because we don't even have a standard distribution right here. We don't even know what the standard distribution is. So it shares the same issues with the autoencoder. That is, it is cannot be fully considered as a generative model because we don't know what the latent space, at least what the latent distribution is. Okay, so to solve these issues, VQVAE actually use a pixel CNN model because we know that our latent is actually a two-dimensional things with tokens, because each entries of the codebook can be considered as a token. So we only have like 32 or k discrete entries of the codebook. So it fits perfectly with the setting of pixel CNN and pixel RN, even better than the original, the actual pixel CNN and RN. The reason is the space is actually discrete here, unlike the actual setting of pixel CNN, because pixel CNN works on image. So it treats the 25 and 60 level of intensity as different tokens, as discrete tokens. But we know that 256 has an older So like the example I showed before, if the ground truth is 100, if my prediction is 99, it is as bad, as poor as if my prediction is like 1 or 2. It doesn't consider the order or the value of the output, because they are all considered discrete. So that's one of the concern that I have mentioned when we talk about pixel CNN. But this one is not the case, because our codebook is considered to be a discrete thing. So that's totally fine. Okay, so the prior is trained by using a pixel CNN. The equivalent part of the variational autoencoder is actually using the K diversion to force the output to be a non-distribution, which is the standard normal distribution. But here, we are actually don't know what the prior the data is. We are trying to train a new a model to tell us what the distribution is. So by combining these two together, we get a very nice model. But I guess the thing that we learn from here is VQ is actually a quite interesting tool to solve our problem. So not only it can be used for VQVAE, it can also use if you are trying to use a GAN, and can be considered as a generic contrasting block, a layer of any neural networks. Okay, so that is about the original VQVAE. So what happens to the VQVAE2? So it actually replace the codebook with another method to actually compute the running average of the updates. Just like we said, the sort of each of the each of the entry of the, we are training the entry of each entry of the codebook by using the mean square error. So it will actually convert to the average of the sample that encountered with. So why not we simply to just compute the average directly without using the optimize? It is the way to do that. So it uses the exponential moving average to actually compute the average explicitly, instead of using the optimizer to optimize and to find out the average. So this is the difference. It makes it more efficient. And the other difference is it has a hierarchy layer. It has more than one VQ layers. And as a result, it also has more. So for each VQ layers, it requires a separate pixel CNN models to do the actually sampling. The good thing is different, because the different layers have different resolutions. It can capture the representation of the image from for different resolutions. So that's a good thing about it, because you remember the original title of the paper is Neural Discrete Representation Learning. So it's all about the representation learning. So by using the hierarchy architecture of multiple VQ layers, it actually learns sort of a dictionary of different resolutions. So that is pretty good and extra things to get. So this is some example not generated by the VQVAE2. So even if with the standard, today's standard, it's still considered to be at least okay, because there are no obvious shortage of this data. So for phase, I think it's almost perfect. Though, the modern day algorithm can actually generate more complicated scenarios, but still, this one is considered to be, I think there's no nothing unusual or unnatural in this kind of image, and it also has, compared to the GAN and other comparable models, it has more variety. Although if in its original form, the quality may be a little bit worse, just a little bit, but it certainly has more varieties. Okay, so it comes with another thing. That's pretty much about the VQVAE, but VQVAE in this paper, it comes with a very interesting tools to do the trade-off of between the fidelity and diversity. So it is usually an issue that comes when we do the generative models. So that usually, if you wish it to have best fidelity, it usually comes with the price with lower diversity. And if you wish it to have a higher diversity, it usually comes with the price with lower fidelities. So VQVAE2 actually present a method that it actually trains another classifier and use this classifier to actually pick, like if I generate like 100 images, I can pick, it can give a rank to the this image, and I can pick the top 3 images. So if I pick the top 3 images out of the 10 images, or pick the top 1 image out of 30 images, or pick the top 1 image out of 100 images, this image is supposed to have a better fidelity and qualities, although it may sacrifice the diversity. But by using this one, we can have depending on your application situations, we can exchange the fidelity with the diversity, and vice versa. So that's an interesting idea for control and a very practical way of, after you have already trained your models, you have make most out of these models. So in image generations or generating models, they usually have many different metrics to measure how good it is. One way to do that is the object detection. We have a precision and recall, which we'll cover it later. But basically, the recall is something that how likely a true image can be generated by your model, and the precision is the image that your model generated. How likely the image that your model generated can be considered as the true image. So that is precision. So it usually also has a trade-off, and you can see that there's a beautiful curve that's showing the trade-off of each of the model. And of course, the higher the model is actually better, because higher the recall, higher the precision is better. And another very common used metric is FID, virtual inception distance, and inception score. So they kind of like represent the fidelity and the diversity. And they are also very often used to do as a metric for how good image generating model is. So we are also going to cover this when we talk about the generative adversary networks. Okay, so that's pretty much about the variational autoencoder. So how long have we been so far? We have already been here for like 2 hours. Okay, so I also go to for the generative flows. So because I have already prepared for it. So this one is also a very interesting idea, and like I said, it could be the next big thing. Okay, so here are a list of reference for the generative flow. There are many different research related to this topic, and this one is a very interesting blog post that introducing the idea. So if you are looking for something that is more soft to read, it might be a start point. Okay, and okay, so this video is a tutorial that is in ECCV 2020. I'm not going to play this video, but you can check this video. From the snapshot of this video, you can see that the quality of generative flow is comparable to, at least for generating human face, it is comparable to what at least for some style gain or maybe the VQVAE can do. So what is a generative flow? So let's compare with other models. So although we haven't officially introduced GAN, but GAN can be considered as unlikely other models like VAE, flow-based models, or diffusion models. It kind of like two-way, the other way around, because in a GAN it has a generator and a discriminator. When training, it actually starts from a generator and output the image and feed the image into a discriminator. All other models are kind of like the autoencoders, start from an image and get latent, and the latent has a decoder to do other things. So, but as the VAE and the flow-based, and actually for diffusion models, they are sort of similar. So if you can see right here, the flow-based model is like by given a image or an X, it may not be just an image, but maybe a video, a music. But I'm just using image as an example of the target that we wish to generate. So if you are input an image into the F, it works like an encoder, and we get a latent. And from this latent, we sort of using an inverse of this encoder, which actually called the flow and the inverse. So we use the inverse and get the original image back. So at the first glance, it makes no difference with an autoencoder. It also has an encoder and a decoder. Only it coded the encoder as a flow, and coded the decoder as the inverse. Other than that, the topology of this diagram looks exactly the same. So the first thing you may notice is that this one is not a square, but this one is. Okay, so that actually means something. It's not just because we wish to draw something different in different polygon shapes. It is because we have mentioned that the bottleneck, which is latent, latent should be bottleneck for an autoencoder. So the dimension of this one is actually smaller than the X. The dimension of the latent is smaller than the X. So that's why we have a small side here and longer side here, and here is also the same. So the reason that this one is exactly the same is crucial. This is because the dimension of the latent space for the flow-based generative model is exactly the same as the input or the X. So that's one crucial difference, because we have discussed that one principle of designing an autoencoder is we should have a small enough latent space. Otherwise, it doesn't actually work. The other thing, major differences, is that this one is F and this one is F inverse. So instead of training a separate decoder and encoder and hope them work like inverse function. So the inverse function means that we are actually expect that the encoder, let's call the E as encoder. So given by given X, and we composite these two functions together, and we have this one back. If by given X, we have X back. So this kind of function is called the inverse function. So we call the D the left inverse of E and E the right inverse of D. So if they can have a both way vice versa, then it calls it a full, or just simply call it a inverse function. So here the F inverse is the two-way inverse function of this F, which means F inverse F X is equal to X is equal to F. Let me put it right here. F inverse F X is equal to X, and also F inverse X is also equal to X. So it's a two-way inverse function, and it is not trained to be so. It is designed to always be the inverse function of F. So the key part of the flow function of flow-based network is that the architecture can be easily to construct the inverse function of this flow function. So that's a crucial part. And as a result, it totally makes no sense to train it as the way that autoencoder is, because there's no training needed. X is always equal to X prime, because it is by design. This is an inverse function of F. So for every parameters, every weight, every theta, no matter what it is, X will always be equal to X prime, because this one is the inverse function of F. So that is actually why we need to have the restriction that the dimension of Z is equal to X, because otherwise there's no possible inverse function exist. So if we wish to have an inverse function exist, the source space and the target space, the destination space, has to be the same size. Otherwise, you can consider it as information. So if we have information from A and transfer to B, and from B to A, if we have to have exact information back, then the size of the B have to have the capacity to store all the information provided by A. Like make a copy. You back up your hard drive into another one. If that one is smaller than the original one, you cannot have a full copy, a full backup, and vice versa. If the original one and the other one, original one is smaller than the other one, then the other one cannot have a backup on the original one. So that's why both of them has to have the same size. So in order to have an inverse function. So although they look pretty, the flow-based model and the autoencoder looks like pretty much very similar and almost no differences. These two are the crucial difference, because you cannot train a flow-based model using the reconstruction laws like an autoencoder. So what are the we'll go into the detail, but let's see what's the benefit of using a flow-based model. So it has an exact latent variable inference and log likelihood of evaluation. So unlike that using for the VAE, the Variational Autoencoder, we have to maximize the ALBL. That is the formula P log px minus something, some K divergence. So we did not optimize the likelihood directly. We are using a estimation also to estimate the lower bound. We optimize a lower bound for the our target, the likelihood. So that's called the evidence lower bound. So we are not directly optimize the likelihood. But for flow-based model, because we have this inverse, so everything is computable. So we are optimize the likelihood directly. So the only let me go through some remarks on this flow models. So unlike by comparing to the autoregressive models, it has the advantage that it computes very fast. But other models like Variational Autoencoder also shares the same advantages. Because this is like the VQVAE, this is also can be considered as a way of learning the latent space for learning and latent. So one important aspect of this kind of model is how good the latent is. So some experiments shows that the latent trained by using this flow-based model can be very useful for some downstream tasks by comparing to like some other models like GAN or something. And which we'll cover it later because a flow requires some spatial architecture. So they might have some potentials to be computed more efficiently. It says it is in memory saving because the gradient can be easily to be reversible. So because the architecture and some intrinsic properties of this kind of architecture, it may have some advantages for efficiency and can save memories. So what is generative flow is? So by considering a generative flow, you can consider it simply is just a function with a continuous function, actually a differentiable function with a differentiable inverse. So because it has inverse, then it has to come with, if the domain is an n-dimensional space, the range must be an n-dimensional space. And you can actually visualize this transformation by thinking of the structure of the space. One way to visualize the structure of the space is by the grid. So you can see that by considering a two-dimensional space, we can have some sort of sense of visualization of the structure of this grid point and the straight line, the vertical lines, because it demonstrates the actually matrix and structures of this distance and angles of this space. So by keeping this vertical line, straight line, and the grid point, what will be these guys after our transformation? So basically, if this transformation is inversible and is continuous or even differentiable, there will has no intersection. There will be no new intersections of the lines after the projection into after a transformation. Although it may look different, but the order of these vertical lines and the straight lines, they're still one by one. They may be kind of warped or get from straight to become more have curvatures, but they will have the same order and they are not going to break down at anywhere. They are not having new intersections at any possible place. So if it is the case, then it is the transformation that we are looking for. So if it is the case, then it has an inverse. So we can actually visualize the inverse by using the same way. And like the variational autoencoder we have introduced right before, the goal is to transform a distribution like here the normal distribution into another distribution, any arbitrary distribution. That is our goal. But for the flow models, we are pretty much kind of doing it reversely, in a reverse way, that we take our data space and by using the flow to get a latent space right here, or to get into a latent space, and we can actually use this result because we already know when we know what f is, we already know what f inverse is. So we need some spatial architecture. In general, it's very difficult to compute the inverse, even if it is possible. But by using some spatial design, architecture, and layer and construction blocks, we are consider only the frame network that it can be easy, so that f inverse can be easily computed. Then, because we already know this guy, and actually we know the gradient of this guy, we can compute the loss directly from the generated z, because we can directly get what back here, and because all we need is this one to be as because this one is not standard normal distribution. All we need is this one is to be standard normal distribution. So everything else can be computed using the reverse function and the function directly. Okay, so because we have all the tools we need, suppose we can compute the inverse of the matrix of gradient or differentiation. So the matrix is actually called the Jacobian matrix. So in order to have advantage of that we are saying above, to do all the computation, we need to have a Jacobian matrix. A Jacobian matrix is basically just the gradient. If we have multivariate function that has a factor valued, so the factor value means we have f1, f2, f3, and fn, and the multivariate means we have x1, x2 to xn. So this guy is called the Jacobian matrix. Of course, because this matrix, it has to have a inverse, the n must be equal to m. So that's another way to see that why the dimension of data space and the data space has to be the same. We need to have, first we need to ensure that the Jacobian has to have an inverse, and second, the inverse has to be very easy to calculate. So in general, it is kind of difficult, so we have to have a spatial designed layers for this kind of purpose. So this one is a popular choice or a kind of standard choice over the layer that used for the flow-based model, which is affine coupling layer. The detailed explanation is right here, but I'll give you some simpler explanation of why this kind of thing is easier to compute the inverse. So let's consider only the system of linear equations. So suppose we have x1, x2, and need to map to y1, y2. So consider our mapping is y1 equals to x1 and y2 equals to, say, 3x1 plus x2. So it is pretty easy to compute y1, y2 from x1, x2. But how about the reverse? So is it easy to compute x1, x2 from y1, y2? It turns out if the formula is like this one, it is pretty easy because we can simply, by given y1 and y2, we know that x1 is simply y1. And after we get to x1, and we know that x2 is simply y2 minus 3x1. The actual construction of the affine coupling layer is a little bit complicated because it requires some exponential to make it more expressive. However, the idea is that if we have some sort of triangular way of computation, that is, although overall it is still a very difficult thing, but we can solve it one by one is easily. Then the reverse is, so I mean the reverse, it can be solved one by one and it will become very easy to compute. As the relationship between a system of linear equation is pretty much, you can consider that a matrix inversion is almost as the same as solving a system of linear equation. So if you feel this kind of system of linear equation is easier to solve, I mean this one, you can easily find out the solution right here. This actually means the computation of the inverse matrix is easy. So in fact, we call this one like lower triangle matrix. So you can see pretty much this one is doing the forward pass. This one is the inverse pass, the backward pass right here. It's actually called the inverse propagations, not the back propagation, because it's compute the inverse function, not the doing the back propagation for the computing the gradient descent. So it's called inverse propagations. So the reason that this kind of computation is easy is because it is a lower triangle. This is diagonal, so everything is lower triangular way of matrix. So if it is a lower triangular matrix, it is easy to compute the inverse. For the same reason that the above mentioned system of a linear equation is easy to solve. So that's a way to construct this one. So it is sort of like a regular neural network layer, except it has some limitations. So the question is how expressive this, or how powerful this kind of layer is, or is this restriction change the power of this neural network? So this is a legitimate question because we actually have the benefit of getting the inverse really easy, but it really has no saying about how strong, how powerful this kind of layer is. So in the history, there are some other additive coupling. For this one is using in nice. This one can be considered as the spatial example of the above the affine coupling. So like the expressiveness or the capacity, more like the expressiveness of this layer is in fact a topic that we should need to investigate. So there are many different designs to claim or to have a goal to have a better expressiveness or more powerful while retaining the easiness of computing or calculating the inverse of the Jacobian. So the other way application is to use for the image, so like using convolution. So the usual problem is that when we do the convolution, we usually do something like we do half the resolution and double the channel. Like this one is 32, and say 16 channel, and become this 16, and double the channel. So we usually wish to have this kind of design to mimic this kind of design when we do the flow net to design a flow network architecture. However, this kind of thing, because the total dimension is smaller, so it is impossible. The best thing we can do is maybe try to make it 64. So there is some standard way or some way to rearrange the things still by reduce the spatial dimensions, but while keeping the total dimensions of the hidden states. So for example, it can change a 4x4x1 tensor and by using it into a 2x2x4 tensor. Okay, so there are some studies of how to apply the same idea but on convolution. And also, if we were using the things like what we do, like y1 is equal to x1 and the y2 is equal to 3x1 plus say x2. If we all the layers we have is something like this one, even if we composite with each other, we still have the first element should be exactly the same, like z1 is equal to y1 and z2 is equal to say 3y1 plus y2. So this kind of network is not that useful because you have to have one dimension to be exactly the same all the way to output it. However, just like we say, we are trying to investigate or seeing how useful this kind of construction can be used for general use. This restriction is turned out to be very easy to overcome because we can change the pattern of the order of the component alternately. Because so we can do something like for the first one we choose y1 is equal to x1 and y2 equals to something other, and for the second one we don't have to use the first component to be the identical one. We can use the second one to be the identical one, so that we can choose z2 to be y2 and z1 to be say 3y1 plus y2. And if we combine these together, we don't have the issue that there are some components that never change. So by combining these things, we might have construct some very useful and very powerful networks. There are also some issues that for other problems, or for this one, it may have something like intentionally keep them the same, but because we have to keep it to be inversible, so it makes sense to keep something that unchanged, and or keep some information that is returned for the different resolution, you can say that. So there are many considerations, and in fact they can construct really very complicated networks. And there are also some multi-scale architectures, especially suitable for image generations. So these are some images that are generated by these algorithms. As to today's standard, they are not very impressive, but So even compared to things like not even the style gain, comparing to say VAE or maybe progressive growing gain, it is not not if we don't really need to use the style gain to beat this kind of generated phases. So, but okay, still the idea is pretty interesting, and it's still not too bad, but it's not that impressive. So there are some motivations and to make it have a better, can generate better quality. One of the famous algorithm is GLOW, GLOW. It actually has a simpler design of architecture, so it is intended to use for image generation. So you can see the basic construction block is here. So we have ACNOM and invertible 1x1 convolution layer and a fine coupling layer. By combining or merging, fusing these three layers together as one building block, this is one step of the flow. So by using this one as a building block, it can design a very powerful architectures and can generate some, I think it's still impressive result like the face we have shown in the videos. So here are some ideas and some computation functions. So by designing all this kind of layers, because you need to compute the inverse function, so you always need some formulas to write down explicitly and to do at least some computations. So these are those construction blocks, which including the activation, normalization, invertible 1x1, and of course it combined with the sort of linear one, the affine coupling layers. And you can see that the generated phase is okay. It's not too bad. And one of the strong point of this model is the latent space. So it also shows the linear interpolations of the phase in latent space between some real images, because it has inverse function. So just like the autoencoders, we can manipulate real images really easily, because every image can be manipulated because we can get the latent from this image. So there are also Flow++, which is also solving certain issues, but we are not going to into a detail. We are going to see the things that on the autoregressive. We'll skip this one as well, because and also we are skipping the VAE. Okay, if you are seeing something that it makes you feel interested, you can still look into it, and we have a reference to the original articles. You can read this through. But the thing I wish to introduce, they are actually very interesting. It's just we have a lot of material we need to cover, so I have to pick some and discuss some of them. So, but the one that I wish to share with you is the FF hold, which is so the above, like FVAE and autoregressive flow models are combining the flow models with other architectures like autoregressive models and of course VAE. This one is particularly interesting, is like combining the flow models with neural ODE. This is because I actually have a note about the neural ODE right here. If you can check about it. But the idea is that if we consider the let me go into it. This guy. The basic idea and the most interesting idea about the neural ODE is that it can be considered as the continualization of residual network. The thing is, this one is an ODE. This is not as abstract or difficult as you may think if you are not familiar with the differential equation. If you consider H as a position in a space, in a three-dimensional space, this guy is in fact, I mean, the t is the time. So ht, the position, derivative of h, the position against the time, is simply the velocity. So we are seeing this equation is simply saying that at time t, the velocity is determined by these two functions. Like we are given the time and the current positions, we have a function to tell us what direction and the speed which we should go right this instance. So we can find there are standard way to find the solution of the h, which is the trajectory of the things, because h is a position, so we have a ti here. So for each time given any time, we can find the position of it, and of course we can find because we have the position of each time instant, we compute the velocity of the whole time, so we can check whether this one is the answer. But the observation is that this one is a long holding observation, is that if we sort of making it in a discrete time, so say from t plus 1 to from t to t plus 1, the differentiation is look like ht minus this guy is like ht plus 1 minus ht. So we keep this one is equal to f ht t. So if we move this guy to the other side, we have ht plus 1 is equal to ht plus f ht t. If we interpret that ht as the hidden state, you can see that we deliberately call it h. So if we interpret that h as a hidden state of a neural network, so this one is h1, h2, h3, and this one is some so this one are neurons, and we have some connection between each different layers. This one is kind of like a race block. For the race block, I mean, we input and plus the original input right here, and this one is maybe a simple MLP, and we get the output and plus the original input right here. So this one is a race block in a architecture of residual network. So this one looks exactly the same. So we have a graph of this one. You can see that. So if we consider discrete time step, then it is a residual network. But if we continualize the time step, so it will become an ODE, and we can actually have a sort of have a network that has infinitely many layers. Although these layers are not totally independent, but because these layers are represented by f, which we already got that f ht. So the theta is not, we don't have infinite many weights. So these all layers have, they're not exactly shared weights, but their weights are kind of depend on each, not totally independent, I will say that. So we sort of have a continuous version of a residual network, and this becomes a ODE problem, and we can actually use the gradient descent to find out the theta. But the issue is we need to compute the backpropagation over the ODE network. It turns out we can use everything can be translated into a language of a differential language. Differential equation. So everything we need can be solved by a off-shelf ODE solver. So everything we need for backpropagation for doing the gradient descent for those theta can be computed if we and by using any ODE solver as a black box solver. So that's the key idea of ODE network, and it actually fits pretty well with the setting of flow network, because flow network, this one is a one-dimensional setting. So the flow can be considered as a continuous transformation from one space into another. So if this kind of a good flow, so they don't intersect to each other and they play nicely, and if we can have a inverse flow, then it can be considered as some sort of ODE. And by using the same tools that already discovered and developed in the ODE network, neural ODE, in the neural ODE, we can use the same tool to solve this problem. And kind of elegant because and actually fun, because this one is something that at least familiar with the mathematicians and some ODE. Differential equation has been applied into many different fields in mathematics, and applied mathematics in engineering. So a lot of people actually has already familiar with this kind of tools. So by translate these seemingly new problems into ODE and differential equation problem, it opens a lot of new opportunities to solve these problems. So it's actually kind of interesting. One way to do that is this algorithm called FFhold, so which is flow plus neural ODE in sort of a straightforward way. And in fact, this way is already get some really good result. And so you can see this one are the formula, and actually we can see the inverse, and we can calculate everything. So it actually translates the problem into a setting of differential equation. So the result is pretty impressive, at least for this toy example. So this data are some of the popular settings for or challenge problems for the toy example. So I remember when I learning neural networks at the very beginning, or at some point, we're trying to design a network that can actually generate something like this one using very simple network. There are some, so we have a bunch of different settings. Some of them are a little bit challenging than the other. So for example, this one is considered to be sort of a challenge, especially when at the dawn of the development of neural networks, people are still wondering what is the expressive powers of some of neural networks. So you can find these samples in the we introduce some like TensorFlow probabilities or PyTorch probabilities, those kind of models, and maybe you can find this kind of distribution in maybe in scikit-learn. I'm not sure, but they are in somewhere. You can find it of them. So as a result of the FFfold, you can see the result seems to be a little bit cleaner than the growth, at least for this toy example. I'm not sure exactly why, but at least we have a beautiful method, and it demonstrates some of the usefulness or superior result, at least for some toy example. So here are some more examples, but and there's one more implementation I'll see. I like this one, the neural spline flows. But the thing I want to share with you is we actually had a homework for flow network, and this one is I'll change it into a hands-on experiment. And this one is for the forward, and the thing is that I have a demo. I have a link that you can have offshore, because I'm guessing that not all of you are familiar with the differential equations. At least not for. I don't think you can just readily have your computer and solve any ODEs without thinking or referencing to the network. So that's no problem, because in these notebooks we have everything in here. So it will give you some idea of what the flow can do, and it has already implemented a simple ODE solver inside this framework, which is TFP, or TensorFlow probability. So by using this simple demo notebook, I encourage you to try to do something like this one, to have an image as your target distribution. So everything is two-dimensional. So have this one as your distribution. You can choose the total example above, that is totally fine. But to make it more interesting for most human beings, or to seeing some things, I think the image of a face or object is pretty interesting. So you treat the intensity as a weight, so you can convert an image into a distribution. Then you use the demo, or use any flow model to actually generate. Use the flow model actually generate the distribution, and check how powerful this flow model can be. So have an idea about that. So just like I said at the beginning of this lecture, the flow network has a chance to be the next big thing. Maybe even replace the diffusion models, or maybe it has some applications that can surprise us, that has application on different unrelated field. Because the fundamental idea is pretty solid and interesting. It only needs some time to have some good implementations. And it actually has shared some similarities with diffusion models. So I really encourage you to have some experience to see, has a feeling and experience of what it is. Okay, so that's all about this week's lectures, and I hope you have a time to enjoy these two hands-on experiments. Both of them are quite interesting. Okay, see you next week.